Good morning, everyone.
Good morning.
Good morning. Okay. Today we are to start our class, our training on the annual IC design. I believe that this is a very good class for all of you, as we want to learn more about annual IC design. So this training about fundamental in annual IC design. So basically, it's a 3-day courses, and I believe that after 3 days, all of you will learn a lot of things. Okay, before we start, I think it's important for us to get to know one another. Right? Okay, let me introduce myself first. Okay, my name is Dr. Tan. Dr. Tan, you can call me Dr. Tan. So basically, I have about 20 years experience, including in the annual IC design industry, plus the academics as well. I used to be a lecturer, okay, in the university, and teach all these courses about annual IC design, right? So, and then I would like to share my knowledge, that what I learned from the academy, from the industry to all of you, right? So that after that, all of you will be able to use the knowledge that you learn, from these courses into your workplace, right? So that all you more effective in your work, when you do a design or do simulations in your workplace, right? So I believe that this course will help all you a lot. So this is briefly introduction about myself, right? So why not we take some time to know every one of you, right? Maybe you can talk about firstly your name, okay, and why you join this course. What actually motivated you to join this course? Thirdly, where you come from, right? Is it from which company you come from? So you can share, these three things to us, so that we can get to know one another during the courses. Is it okay? Okay. I think we start from this gentleman first.
Okay. So hello everyone. My name is Jackie. Fresh graduate from University of Malaya. So I just recently joined in Phoenix, and then the reason why I'm interested in joining this class is because I actually don't have any industrial experience. So this class will be a good opportunity for me to learn the industrial side of annual IC design.
Okay, that's great. That's great.
Looking forward for the class.
Your name is Jackie,
Yes.
Okay. Nice to meet you.
Nice to meet you.
Okay. So how about you?
Okay, hi, my name is Daryl. I'm a recent fresh graduate from Asia Pacific University in mechatronics. Recently, I joined in finance as a graduate trainee. But however, in my course back in my in mechatronics degree course, for that one, there's not much in-depth exposure when it comes to analog IC design. So I believe that in this course, it will give me more insights to into the analog IC design realm.
Okay, thank you. Okay, your name is Daryl.
Daryl.
Okay, nice to meet you.
Okay, nice to meet you. Okay.
Right, hello everyone. My name is Gim, and I'm fresh graduate from Asia Pacific University as well. And I moved to Penang 3 weeks ago because I originally was living in KL. And yeah, the reason why I joined this course is because I find analyzing design quite interesting, but at the same time challenging. So, and I would love to explore into this field. So that's the reason why I joined this course. These courses. Yeah.
Okay, that's good. So I believe that everyone join this course with certain intentions. Okay. But I think you want to learn something new, right? So I believe that this is the right course for you. Okay, I believe that after this 3 days course, you will be more effective designer. You will contribute more to your company as well, right? So the brief about the courses you want to learn. Okay, this is some content that I want to show you, right? So basically, the key things that you can see clearly.
I want to zoom in a bit more.
Okay, zoom in a bit more. Okay, let me zoom in a bit more. Okay. a little bigger. Okay. So basically, you learn about many things today. Example, single stage amplifier. You learn about common source amplifier, where you learn about small signal model. Everyone of you going through small signal model before?
Yeah. Yes.
Right? Interesting, like small signal model. Right? I think I ready to say that. Then you learn about a lot of things. You learn the common source amplifier. You learn about the current mirror. You learn about the differential amplifier. What is the differential amplifier? What is the single amplifier? You learn as well the classical two sets of amplifier. Example, what is negative feedback? You know? What is bandwidth estimation based on the closed loop model? And also we learn about how to stabilize your negative feedback, your op-amp, right, with the frequency compensation. And also you learn about the what is a body plot. Everyone of you learn about body plot before? Body plot? Everyone learn before?
Not exactly sure if I heard of it before.
You learn about pole zero, right?
Zero, yes, yeah.
Yeah, this is something you learn as well. Alright, this is something interesting. And so learn about the class AB output amplifier.
Okay.
What is class AB? You know, sometimes you learn about class A, class B. And then what is the class AB? Right. So all these things basically you learn in this course. Right. So we start from, but before we learn all these things, we start from something very basic. Right. Very basic. You know what is the most basic thing? The most basic thing in electronic device.
BJT.
BJT. Before BJT?
PN junction.
PN junction. What actually PN junction from?
Diode.
Yes, diode. Right? So the most basic electronic thing in the world actually is a PN junction. Actually the one from diode. From diode it form what?
Transistors.
BJT, right?
BJT, yeah.
Right? It's like the more, what we call that, the most primitive device in the world actually is a PN junction. Right? You realize that in IC level, CMOS transistor level, look at the cross section of the CMOS layout. Right? Do you see a PN junction?
Oh,
Yes.
yes.
Yeah, right. Remember by this, right? Your substrate, your source and drain. So basically, let's say you look at MOS. Your source is the M plus. Your substrate is P sub. P sub. And then it's found in PN junction, right? This PN junction, you need to reverse bias. There might apply a test of you. Right? If you look at the IC level, inside IC, everything is PN junction. Right? And also about ESD is a PN junction also. About the zero diode, everything is about PN junction. That's why you must, before you design any electronic circuit, first of all you must be the expert in the PN junction, or what we call it at the diode, right? Actually, you know this is a curve for the. I think everyone learn this in your university, right? But how much you understand about this curve is very important, right? And normally this curve I can teach about 3 hours. this talking about this IV curve for the device, right? So every time I teach the people, I always say focus on the IV curve, right? What is IV curve? IV curve basically is a current versus voltage for any electronic device. It can be diode, it can be transistor, right? So before you use any device, make sure you understand about the IV curve for your device. Okay, you look at, everyone know this is a diode, right? This is IV curve for diode. So the first question I will ask anyone when I interview people also. Okay, this is the first question I ask. Diode behave as a voltage source or current source? Let's come back to all you. Okay, is it very hard?
aspect, it's a current source.
Current source, huh? Okay. You?
I also think it's a current source.
Current source. Jackie?
I think it's a voltage source
Why voltage source?
because it's fixed voltage.
Okay, never mind. We look into, before we look at answer, right? Okay, we look into the definitions. Okay, of what is voltage source and what is current source. Okay, first maybe I ask one of you. What is voltage source?
A voltage source is a supply that generates a specific amount of voltage, but then doesn't matter how much current you actually source from it.
So the voltage the voltage will be constant.
Voltage will be constant. Yes.
Okay, so it means something like this, right? Right. So in respect of the current draw from here, right? The voltage will be constant, right? What is the example of the applications for that
Application for
voltage source?
a voltage source.
You can think of
A car battery.
the battery, right? Remember, the battery, no matter how much you draw the current from the battery, the supply is still the same, right? Let's say 3.3, it's still the same, right? Whether it's 50 milliampere or 10 milliampere, 3.3 is still 3.3, right? Like you design LDO, right? So whether it's 150 milliampere, 10 milliampere, the output still
3.3.
3.3. This is what we call a voltage source. How about current source?
Current source supplies a specific amount of current, but it doesn't matter how much is the potential drop. The potential difference between the two ends of the current source.
So current still the same, right?
It's current still the same.
Okay. So normally we model this as a voltage source and current source. Look at the screen here. Voltage source, you model a small resistor, Rs. This ideally is 0, right? And current source, you model it as a current source parallel with the resistor. This is modeled as a very high resistor. This is very small. It means that by right, when you at a battery, it should not have ideally should not have a soft resistor, right? It should be very small, or ideally should be 0, right? So now, okay, based on definitions that we give, what is a voltage source, what is a current source, you look at the curve again, and decide, whether your answer is correct or not. Here, for bias, right? So, voltage increase, right? Current almost constant, right? No, sorry.
It will be exponential.
Like voltage almost constant. I mean, you increase voltage almost constant. But the current, right, exponentially increase, right? No, this one almost very sharp, right? You see, right? Okay, based on this, now make your judgment again. Diode is a voltage source or current source? I think this one you want to define, right? Better you want to define, right? What is voltage source? Take your time. Now to think about it.
I have doubt already. Because right, if I want to label it as a current source, I want it to supply a specific amount of current. But then no matter how much I want to change the voltage, but then in this case, right, if I were to manipulate the voltage, right, the current will increase very exponentially. So in this case, if we follow the definition of an ideal current source, whereby the current is like stable, then it does not fulfill that condition, I think.
Okay, yes.
But for a voltage source, this one I'm not exactly sure at this point. I'm not exactly sure.
How about you?
So we're looking at this graph. Since the voltage somehow gets stabilized no matter what my current is, so this should be a voltage source.
Okay, Jackie?
Yeah, it is a voltage source. voltage source of 0.7 volt because I only work at the voltage.
Okay. Yeah, correct. So actually, what is source? Right. You can see that it's a battery, 0.7 volt. How much it can be? 10 milliampere, 100 milliampere, 1 ampere, doesn't care. It still maintain 0.7 volt.
Oh, okay, okay.
Right. So obviously this is voltage source.
Okay,
Right.
understand.
So this is something that learn more than you still, diode is a voltage source. In fact, I asked this when I interview a lot of people. This is the first question I'll ask everyone. Okay, what do you think about diode? Is it voltage source or current source? I can tell 90% will answer with current source. Don't feel bad, huh? 90% of people will answer as a current source. Or no? Only 10% like Jackie answer as the voltage source.
Because I got it wrong before.
Okay? So this is very important things. That's why, this on right, when we model this resistor, how we get this resistor? Let's say I model the diode. Okay? How we get this resistor from this curve, the RC? How you get this resistor?
Current multiplied by voltage.
This one we saw the voltage source in series with the resistor, right? So how you get the resistance from this curve?
It's the between 0 to 0.7, that's the voltage, and then the current multiplied with that voltage, and you get the resistance.
Yeah, correct. Actually, you measure the slope.
Oh.
No? The slope actually represents your resistance or source resistance for your battery. No? You measure across it. Actually, not that sharp. In particular, not that sharp. You measure like that. You make a tangent there. The one that's going to tell you what is your R on for your diode. No? That's why ideally, when you see when the R is 0, right, you see that because R is V divided by voltage divided by current. If this one delta V is 0, because when your current change, the current can be delta 100 milliampere. But what is your V? Delta V is 0. No change, right? I mean delta V R is delta V divided by delta I. If delta V is 0,
Did you say 0?
right? Bingo, right? Yeah, it's easier than that. So that's why I say sometimes you can spend 2 hours on this curve, talking about this curve. Right. So this is very interesting curve about IV curve, and this is diode actually related to all your PN junction. Right? That's why you look at the diode formula, you still remember the diode formula is very complicated, right? There's an exponential there, right? That's why normally people just normalize it as simple as in calculation, right? People just put the example of diode. Normally people put that 0.7 plus R to make it linear. You look at the equation for the diode. Let's say it's exponential there, right? You put in KVL, you make your calculation become complicated. That's why people normally model as a diode model as a voltage source. Let's say voltage source is 0.7 plus a resistor. To model as a diode. So you make your KVL and circuit become more easy. Right? So this is approximation for the diode equation. Okay? Understand that? Clear? So now look at here. Okay. I think this is a good question. Okay. You know that I asked you this question. You know what is a linear device?
Something which is proportional to the other variable.
Actually, linear device refers to IV current voltage for the device, right? When you say linear device, voltage increase, your current increase. You know, any device in this world behave like this.
Oh,
Resistance. Okay. Now the question. Is capacitor and inductor being considered as a linear device?
No, I don't
No.
think so.
Okay. It depends how you define it. Because for capacitor, what is a capacitor?
It's a device to store charge.
I equal to C divided by E.
Yeah.
Okay. Is dividity is constant?
Constant.
It's still a linear device, right?
Right.
Right? Remember? Capacitor equal to I equal to C dividity. Right? Let's say your dV/dC is constant. Basically, I is still linear with dV/dt. Correct? Because you no way to make your capacitor inductor always dependent on time, right? You know? Correct? So actually, in other words, actually, it's still considered a linear device capacitor. You look at I equal to C dividity. Right? How about inductor?
Same also can be linear.
Yeah, can be linear also, right? That's why we can see that resistor, capacitor, inductor, basically is considered is a linear device, you know, for all of us, right? So I introduce all these basic to all you so that all you understand, you know, the concept electronic, right? Why actually the linear device, or why actually a non-linear device, right? Okay, now we go to non-linear. Okay, can you tell me maybe one device is non-linear to convince me you know about that?
Transistor.
Okay, I will ask another transistor, yes. Examples, MOS. Can you tell me why MOS transistor is a non-linear device?
Because the formula for calculating the
ID.
the drain to source current has a square then.
Yes, correct. Because we will refer to the I versus voltage, right? Right. Then basically you can see the square there, right? Is a VGS minus VTH square. So basically it cannot be linear. It's a non-linear device, very obviously, right? BJT the same also. It's a non-linear device. So I can say that all these passive components like resistor, inductor, and also the capacitor is considered a linear device. The rest of the component, like MOSFET, CMOS transistor, BJT, is considered as a non-linear device. Okay, is that a concept?
Yes, sir.
So this is will help you to move further, right? So any question you want to ask to more clarify? At least one question. If I cannot answer, Jackie can answer.
No answer.
Okay, try to look into. I give 1 minute to think. At least one question.
So I have one question. So for the just now the I dash V characteristic, right? The graph. Yeah. So it doesn't matter for linear device or non-linear device. The slope is always the resistance, is it?
The slope, yes, over resistance, right? The slope over resistance.
So diode is also a non-linear device.
Diode, actually it's a non-linear. Yeah, correct. It's a non-linear. You look at the curve, you know it. But we linearize it by using the approximate like voltage source in series with resistor. By default, diode is a non-linear device. As you can see here very clearly.
So you're trying to say that if let's say we put another resistor in series with the slope of that resistance, then the whole characteristic will change to a
No, that resistor is something we model it. It's an AC model. It's not the real R there. Or something we make it a model. You know? So we put that, actually we put that to linearize the whole thing. You know?
Because the gradient keeps changing, so how do we find the R? Does the RS also keep changing when we want to model it?
That's why normally we put at the R that where your current that you're going to use in your circuit.
Or just for that point?
Yes, correct. Example like you targeted at you use a 1 milliampere, you target at that point, what is the tangent?
Okay.
Right? That one actually represent your R for the circuit. Right? Because no point, right, if your current is let's say 100 micro here, no? You put the R for here, no? So it doesn't make any sense.
So based on this graph, the resistance will keep on changing based on where the point of the graph is.
But when you go to here, it's no much changing. But here, of course, right? When you go here, actually no much changing. Because you can see that the delta V almost constant, almost zero, right? So it depends where you place your current is. No, you say yes, yes, you know, you change a lot, close here. But once you go here, you can see that the delta V almost zero, no changing, right, with the current. So you can see that at this particular point, the R will be quite constant. No, no, got a point? It's a good question. And here is a part that actually reverse bias, right? Reverse bias, especially there's still some leakage current. Okay, a lot of times we thought that we use here only. In fact, I tell you, this part even more, we use a lot also. Where we use?
Protection.
ESD. You go to study the ESD, right? Basically, you had an balance breakdown. Basically, you use a lot of this portion. You really go to study the ESD, right? So basically, for us, right, as a design engineer, we use whether forward bias or reverse bias, 100%. To really in the design.
One question, what does ESD stand for?
Electrostatic discharge. Example like remember when you touch your car, you feel a shock, right?
Okay.
It discharges through your body to ground, right? It's like we touch two potential difference, right? You touch it when you are at the low potential, right? So actually the charge will discharge through you to the ground, right? That's why in the IC, right? You know IC got many pins, right? Actually, as accidentally touch two pins, right? So it will cause ESD, you know? So it might destroy your chip without the ESD protection.
So it's the same thing as you take two material and you rub it, then you have some charge on each other.
Yeah,
like that.
correct.
Okay.
So basically, we want the charge in IC, right? We want the charge not to go into your IC, but go to the ground to protect your IC, right? The charge actually in the IC level can interpret the current, right? The current actually inject into your IC input actually will destroy your IC. So we want to create, actually ESD is create a low impedance path to ground.